So much in resonance, but our next presenter, Daisy Fox, another IOP coach, is going to tell you about resonance and how it's involved in music and how you get to hear music through resonance effects. Over to you, Daisy.
Thank you. Right, I'm just going to hopefully share my screen with everybody. Bear with me 1 second. Sorry, I'm just trying to get the PowerPoint going.
Oh, there is a bit of delay, Daisy. We know it's
that's
working.
okay. Right, can I just check that people can see my screen and that's okay?
Yep, that's working, Daisy.
Super,
that's good.
Thank you. Okay, so I'll introduce a little bit about myself. I'm Daisy Fox. I work as an IOP coach, a bit like Kerry, working with physics teachers in the sort of the North region, the Northwest, sort of Yorkshire and the Northeast. One of my other roles, as well as thinking about physics in schools, is also thinking about inclusivity, and particularly with gender bias and gender balance. And it kind of matches my philosophy for going into teaching, really. One of my philosophies for going into teaching was to try and make physics as accessible to students as I possibly could. And Kerry will put out the links to this as well. If you haven't seen this before, these are the top 10 tips the IOP suggests for inclusive science teaching. And it's based on our work on gender balance and you know, how to encourage a more diverse group of people into physics. In this presentation, I'm specifically going to try and use instruments as an example to show students how science relates to their kind of everyday lives. Similarly to Kerry, sort of my interests are a little bit musical as well, except mine aren't as diverse as Kerry. I'm very, very much focused on the guitar, and this is my daughter's one. Ironically, she insisted on having a pink one, so well done there for us with yeah, that in the house. But yeah, I think when I sort of started teaching, you know, sort of as low down as Key Stage 3 and looking at sounds and introducing the idea of how we heard sounds and vibrations, I just took my guitar in. And what was quite interesting was, as a PGCE student, I remember my sort of mentor turning around to me and saying, why don't you ask them what instruments they play, because actually they can bring a wealth of stuff into the classroom as well. And that was a real sort of eye-opener for me, and something I hadn't at that point thought about. And now I kind of think, why wouldn't you bring you know, why wouldn't you bring their experiences into the classroom as well, and sort of really make it relevant for them. So if we start off thinking, sort of before we get to resonance and start thinking about natural frequency, you'll should see on the PowerPoint that I've got a picture of a bell and a frying pan, and we're trying to get across the idea that if I were to strike them at the minute, so loud sound coming, okay, but the sound of the bell being struck compared to the frying pan being struck make very distinct and different sounds, and I know Phil's going to talk about this in sort of in his session later on. But what we're essentially observing there are those objects' natural frequency. Oh, I don't know what I've done there. I don't think I meant to do that. Can you still see my screen okay? I've just gone massive. There we are, I'll move myself down there.
Yeah, we can still see your screen share.
Oh, perfect. On my screen, it was just a big version of me, and that was quite sort of nerve-wracking. So the natural frequency is an object, is a frequency at which an object vibrates when it's disturbed by a force. And we have to be a little bit specific here, because we're thinking about, in the case, for example, of striking the bell. I'm striking the bell, and then that force is removed, and the bell still continues to vibrate and to oscillate. Compared to if I have something like a rattle, I've disturbed the things inside the rattle with a force, but as soon as I took the force away, those objects stopped vibrating. So they're not oscillating or vibrating at their natural frequency. So when it comes to thinking about musical instruments, the sort of two examples we'll sort of look at here, and you know, for those of you who play different musical instruments, sort of like, you know, wind instruments or brass instruments, you'll sort of have the context of this in your head. But one of the things we think about is that, you know, if we consider a piano, for instance, a piano will have a string associated with each of its keys, and those strings will vibrate at a natural frequency when they're sort of, you know, they're beat by pressing the key. Similarly, on the guitar string, the guitar strings will like sort of vibrate or oscillate at a natural frequency, and we can change that natural frequency on the guitar dependent on where we put our you know, sort of fingers on the fretboard. Now, thinking about how this then applies to resonance, when we've got resonance, we're talking about this phenomenon which occurs when the frequency of a force vibration on an object matches the natural frequency, and it causes a dramatic increase in amplitude. So what I'm going to attempt to do now is just for a moment and stop sharing my screen, and I'm just going to switch my webcam over. There we go, and hopefully now what you should be able to see is a setup of 2 tuning forks and a ping pong ball. Kerry, would you mind just confirming that people can?
That's working, Daisy. We can see that.
Fabulous. Okay. So this is sort of quite a standard experiment I would use to sort of show resonance. And essentially what I'm going to do is strike the tuning fork on the right hand side of the screen with the hope that it's going to make the ping pong ball on the left sort of bounce around a little bit. So here we go. Let me see. Okay. Now, typically one of the misconceptions that students would have here is that the frequency of that first tuning fork has nothing to do with the fact that the ping pong ball is moving. They are kind of familiar with the idea that the first tuning fork is causing vibrations, it's causing air molecules to vibrate, and they think that the ping pong ball is just responding to that regardless of the frequency. But what I'm now going to add to it is this little clamp. And so I'm just going to put a clamp on here as well. Okay, and what we should now observe is that the frequency of that first tuning fork has now changed. And now the ping pong ball isn't jumping around in the same way that it was before. So I'll just take the clamp off again so we can see the difference. Okay. So one of the, you know, so there's a few things of physics going on here. Obviously, we've talked about resonance, so we've talked about the fact that both those tuning fork frequencies have to be the same. So we're forcing, you know, sort of vibrations at sort of natural frequencies. But what we can start to do now is kind of try and apply this to the guitar a little bit as well. So the guitar has effectively a sort of resonance box in it. And what I'm going to do now, and hopefully you can, you know, you'll be able to see this demonstrated quite well. I'm just going to put a scarf now inside the resonance box of the first tuning fork. Now, when we practiced this earlier, what we found was that, and if I was doing this like sort of in a classroom session, you can hear the change in amplitude of the sound. What we discovered when we were practicing this before is that some computers have a sort of a bit of an equalizer, and you won't be able to sort of hear that difference in sound. So what I'm hoping we'll observe is that we should see a smaller oscillation in the ping pong ball. So we're going to use the ping pong ball to try and demonstrate this effect. A smaller sort of like, you know, oscillation of the ping pong ball, and as we take the scarf out, hopefully we'll see that oscillation get bigger. So here we go, we'll give it a go.
Yeah, that's really clear, Daisy.
Brilliant. I'll just try it one more time to see if I can get it going even better.
Yep, we can see that working really well.
Brilliant, thank you.
And some people are hearing...
Because some people hear it as well. That'd be, yeah, that's really good to know. I'm just going to swap my webcam back so it's on me. But obviously, you know, for instruments like the guitar, this has a really big advantage because it, you know, we can start thinking about amplitude and making the sound louder. It can have hindrances in music as well, because like sort of where I've forced that first tuning fork to oscillate and it's, you know, it's made the sound I wanted it to, the opposite can happen. And if I was like, you know, like Kerry and more vocally inclined with my music, I could actually try and sing the frequency. Oh, am I still here, Kerry?
Yes, you're fine. You're fine.
Oh, it's okay. Someone I saw it just popped up in the chat box.
They have. If you've got a problem, if you want to put it in the chat box, and I'll try and help you.
No, that's cool. Yeah, so one of the things you can do in reverse as well is actually try and sing at the natural frequency of this tuning fork into the resonance box, and you will get the tuning fork to oscillate because now my voice would be forcing the vibration through there. And one of the conversations we were having about, and it's been quite interesting whilst I've had the tuning forks like sort of set up on the desk next to me, is that when I'm speaking, if there's an element of my voice that matches that frequency, I can hear, and it might not be coming through on the computers, but I can hear that tuning fork start to oscillate and start to make a sound. We were having a conversation, a colleague and I who plays the piano at home, and he was saying that one of the things he's realised that if he sneezes, some of the strings on his piano will start to resonate and vibrate as well, and sort of get a sound there. You know, one of the other things that I sort of, and I'm not a harp player and I'm not an expert on how harps work, but I am aware that harps actually have, I think, like a something that basically means that if you're playing one of the strings at the top of the harp, it doesn't make a string further down the harp sort of start to resonate as well. So resonance can be really important with music. It can sort of have some, you know, sort of cause some issues as well. Now, I'll just put my screen back on. A lot of us obviously are trying to figure out how to do some of this at home at the moment, and I think I saw it pop up in the chat box. But this is a similar experiment that you can try, or you know, get your students to try at home, or if you've got kids at home yourself, you could sort of try it out with them. We've got a series of these Marvin and Milo clips and sort of snippets. They're available. You know, we've got a link for all of these, which I think is going in the chat box, sort of as I speak, hopefully. So yeah, so these are things that you can try at home if you don't have access to tuning forks at home or instruments or anything like that. You can start to see the same type of effect coming through. So that was a very brief prelude, let's say, into like, you know, sort of using instruments to support the teaching of music. I'll sort of let you know if there's any questions, then I'll sort of have a quick look at the chat box. But Kerry, I know you're sort of organising questions as well. That's it from me. Thank you very much.
Thanks, Daisy. Yeah, there are no particular questions, just lots and lots of people loving your demonstrations of the tuning fork. People going to head out and buy it immediately, it would seem. It did work really, really well.